All right, from section 1.5. On 27. Wow. Okay. Freeze. Well, how about let's just fill in the part B was you just plot those points then that you fill in the table. Yeah. So could we just check the points and see if you agree? Okay. So we're looking at the graph over here. That's F, and then we're trying to find the slope. So this is just practice at doing the sketching a tangent line and doing rise over run kind of a thing. Okay, so what did you have for the first empty box at -1? What did you have for a slope there? Anybody? 1, 1.5, 2, 2. Okay, now, let me, let's go back to Mr. Camera here. All right, so if we okay, so here at -1, if we put a tangent line in here, starts about here. If I go over, and let's see, each one of these looks like it's about a half. So if I go over 1, that would be going over to here. Wow, that's kind of hard. Let's go back. Let's go back 1. So if I go from this point at -1, if I go back this way 1, it looks like I go down 1, 2, about 3 boxes, and each box was what? Half. So 1.5 might be good. So 1.5, right? So over 1, I always try to do a run of 1. Okay, so 1, 2, about 3. So I have 1.5, somewhere in that ballpark. 2, I'd take 2. I mean, again, what I'm going to look at on the test, on the quiz, is I'm going to look at your tangent line that you kind of sketched in there, and then I would actually draw in your slope triangle too, and then there you go. Okay? So what about the next box? At 0. What do we get? My line that I have in here looks like if I go over 1, it'd be down about 1, 2, 3 boxes, maybe a little more, almost 4 boxes. So about -2, -1.5, somewhere in there. Brittany, how are we doing? Is this seeming reasonable?
Yeah.
Okay. And then, okay, then we got the next one. Then at 2, 0, looks like a slope of 0 there. And then, okay, we got the next one. And then at 3, so this line up here, so let's see if I go over 1, it's up about 1, 2, 3, kind of 1.5 to 2 again. Is that reasonable? 1.5 to 2. And then it's just plot those points. Make yourself a little graph and plot the points and see what it looks like. Okay? So we're going to do more of that today with looking at an F graph and then looking at an F prime graph. But what I want you to get out of number 27 is understanding that here's an F graph. We look at the slopes of the F graph and we plot those y values and we get the derivative graph. Which yesterday we learned that the sine graph has what for its derivative? Cosine, right? If you plot the slopes of sine, you guys that were gone, if you plot the slopes of sine, you get the cosine graph. It's kind of amazing. Okay, so we're going to be doing some more of that. But one of the things that we will do in the next chapter, or in the next quiz, is something like that. Maybe not where you plot them, but where you have to sketch a tangent line and kind of estimate. But the main focus in today's homework, the main thing we worked on was this idea of actually calculating the slope. And so the main thing I wanted you to get out of today's is that doing the slope between 2 points is how we can estimate a derivative, the slope of a curve. Because if I want to find the slope of a curve, what I really do is I find the slope of that tangent line. Understand that that's the same thing. If I ask you to find the slope of the curve at 1, that's the same as saying find the slope of the tangent line at 1. The slope of that tangent line is the same thing as the slope of the curve. That's what we mean. Now, we need 2 points to do that. So what we have said is do what to get those 2 points? pick 2 points really close. We said that on day 1. So this section's really nothing more than what we learned on day 1. Pick 2 points really close. That's all it is. Okay? And do a slope calculation. Now, what we remember is that when you pick 2 points, you're picking 2 points on the curve, not on the line, because we don't know 2 points on the line. We only know that one. But we do know all the points on the curve, because we can get them from the equation or the graph or whatever. So pick 2 points on the curve, and if you connect those, if you zoom in far enough, it basically looks like a line. If you do that slope, that's basically going to be the slope of the line. Now, we don't want to get too hung up on picking points on either side. Would it matter? I mean, couldn't I just pick this point and do the slope between those? If I zoom in far enough, wouldn't that be good enough? I mean, if I zoom in close enough to this point and then pick one just to the right, that would be good enough, wouldn't it? I mean, so, yeah, it's nice to pick one on either side. Might be a little more accurate. But if we zoom in far enough, it really doesn't matter if we pick them on both sides or if we just pick the point that is tangent and then one other point. Doesn't really matter. But we need 2 points. All right, so what else? Like, for example, another class asked about number 10. Just talk about that one a minute, okay? Because to me, number 10 is really the key. I mean, it's just, here, I want to show you on your calculator what you're going to do. On the next quiz, if we do a calculator part, this is what would be on it, okay? Now, I don't know. We may do a no calculator one on the next quiz, and we may not do this, really focus that much on this section. We might focus on sketching that tangent line and estimating that way. But we may not focus that much on just plotting in these points because it's more the concept than it is actually doing it. I think everybody in here can pick 2 points, do a slope. I mean, that's not really a calculus thing. It's really more an algebra thing. And so, but that's kind of the focus on the homework. So on number 10, they ask you to estimate f prime of 1.5. Now, what was the function? Well, it was x squared, right? For problems 1 through 11, the function was this, f of x equals x squared. Okay? So, it says estimate by zooming numerically. Now, all that means is pick numbers close to 1.5 and do a slope. Now, so what I want to do is, Joe, you're going to be our presenter here, and I want you to go into the graph screen here. Just go, that's cool. Tell us how you did that. Table, but how did you get the split screen?
Comes up with the option.
When you click on table? Yeah, that's kind of cool. Like we could have done it yesterday, but I wanted to say I kind of like it when all those points were there. Yeah, I think you hit Control. What'd you do?
I just
deleted, just cleared everything. Oh, move table. I think there's a Control.
Control T was the prompt.
Oh, Control T. Okay, Control T. Will, so like if you hit Control T right now, I think it brings up a table, doesn't it? Just hit.
Yeah.
Control T brings up a table, and Control T will get rid of the table. Cool. Okay, good. So that's kind of nice with the graph, be able to see table values. Go into F1, tab in there to F1 now. Everybody else can do this too. Let's put x squared in there as our F1. Now, to be honest, you're probably not going to do this a whole lot. You know, like I'm not going to require this on a quiz necessarily, this whole zoom in until it's aligned. I mean, I might if there's a part of that, but probably not. You know, some of the things we do because they conceptually help us understand the things we need to do, right? It's not just about what do I need to know for the quiz. What do I need to know for the quiz, right? I mean, hopefully we learn things, and then we can handle the stuff on the quiz because we understand. All right, so we plug that in, and whatever window doesn't really matter. So let's trace to 1.5. Okay? So we trace to 1.5, and this might be a good time to hit enter twice so it sticks that point actually on the screen for us and keeps it there. This would probably be a good use of that. Okay? Now let's go to menu and zoom, and let's zoom in, and it gives us that little magnifying glass. We put it right over the top of our point. We hit enter. And this is kind of like we did in Appendix A where they asked us for a window that was centered until that line looked straight. We actually had one of those in our homework. Number 14, was it? Or Yeah, number 4 is kind of the same thing. So we zoom in a few times, zoom in till it looks straight. What I usually do is zoom in till it looks straight, and then zoom in one more time. But, you know, just for good measure. Okay, now that might not be right in the center of the window, but good enough. Good enough. Okay? All right, so it looks straight. So the idea there is then that we've zoomed in, just like on the board here, and that tangent line, if we were to draw a tangent line on that parabola, that and what we're looking at would be essentially the same thing. All right, so now what I could do is I could try to trace a point on both sides of 1.5. So let's don't use the arrow trace. Yeah, see here, well, yeah, you'd have to go into trace step. Okay, we'd have to tell it, yeah, right now it's set on automatic, which most of the time's okay, but for this wouldn't be any good. So you could set this. Now, you don't have to if you don't want to, because we can just type in whatever number we want. But go ahead and hit your right arrow there. Or actually, I think, yeah, enter a value. This isn't something we use a whole lot. So go ahead and just type 0.001. And then OK. All right, and what that means is, now, so go ahead and go back to trace, type in your 1.5. Okay, so what we've done is controlled now when we hit our right and left arrow, we've controlled what it's going to do. So now you're setting at 1.5, hit your right arrow now. Now, okay, now that's because of our float. Okay, so we need to fix this, and I don't know. Go to, there's 2 places that I want us to go. First of all, let's go up to your scratch pad, up where it says scratch pad. Yeah, go up to there, pull that down, and go to settings. This kind of drives me crazy because there's so many different places here we can set these float things. Go to document settings. And some of you guys ran into that with that scientific notation. Okay, we're on float 6. Let's change that to plain old float. But I don't think that's going to fix it. I think we want it on float anyway. So let's go ahead and do that. And I would change it to make default. I would go ahead and choose make default. Okay. But then, see, that didn't fix anything. So somebody in the other class found this, and some of you guys may know too. Go to menu right now, and go down to settings, and see we're on float 3 there. Now that might be what happened to some of you guys on that graph thing when you trace. But, and so maybe that's what's going on there. But it's funny that it wasn't that way for everyone. So
Do you want it on float 3?
We don't want it on float 3. We want it on plain old float. I can't think of any time here we want it on anything except float. Okay? We want as many values as it'll give us. And then make default. Okay? All right. There we go. Now we're getting a few more values. So now arrow back so you get to the, there you go. Now, did you put 0.001? You did. Okay, that's correct. So, what I'm going to do now is I'm going to write down that y value. So what is it, 2.253? Okay, and the x value was 1.501. Now trace, okay, he's done it for me already. Now I'm going to trace back to the other side of 1.5, which is 1.499 is the x value, and 2.247. Now I'm going to write that down. And you would want to have copied that down yourself. And now let's go to the calculator side of things. And let's type that in. Now he went ahead and just did the top. And now he's going to divide by the bottom. Or you could have hit Control Divide, given yourself the whole fraction and done the whole thing. Matter of fact, why don't you do that? Go up and, well, never mind. Never mind. We'll do that next time. And he gets 3. Everybody getting that? Something similar to that? That's zooming in numerically. We just zoomed in. Now, did we really need to zoom in to know that 1.501 was close to 1.5? And we really didn't need to go to the graph. Zoom in, and see that. I mean, right? I mean, we understand. So the concept is, so we're not going to live, from here on out, really, we're not going to literally zoom in on the graph. But figuratively, we're going to zoom in on the graph. We're going to just pick numbers really close. Now, let me show you a couple things that you could have done here that would have made life easier. So we wouldn't have had to go to the graph screen. What we could have done instead is, Joe, type define space, which is the bottom right-hand thing on the keyboard, f of x. You don't have to do f1 or anything. Just we're going to define f of x equals x squared, and hit enter. So, being in function notation, this is going to be handy for us. Now, what would be a nice way, instead of figuring out this y value, for me to type this y value? What would be another way to type or write the y value at 1.501? F of 1.501 minus f of 499 over 1.501 minus 1.499. I would like to get you used to that notation because it's so handy, and it says what we're doing. We're subtracting y, subtracting x, so go ahead and do that. Now hit your divide by, so let's do it all in one fell swoop. Whoops, 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 got to go outside the parentheses for that divide. Okay. Well, that's probably not going to work either. You're going to need another right. You're going to, before the divide, you're going to need another right to put all that. There you go. Now divide. And control divide might have been helpful there too. I think, yeah. And where he's going to need a parenthesis on the bottom, isn't he?
And the f of 1.565.
Oh yeah. Okay, so let's come back to here, Joe. Come back to here, in front of your 1 and hit a left. Yeah, see that right? Okay. And then change that to 1.501. Now, has he got it? I think. Oh yeah, you got to divide right here. Tough being the presenter, man. All right, hit enter, and then we'll see. Yep, there we go. Just where we want. See, but see how much quicker that is. But we're still doing the same thing. We're zooming in. So that's what means zoom in numerically. Okay, which means get in there, get some points close to 1.5. Now, they also had a table for us back on page 48. We could have used values off of there. Maybe you did that. Okay, we could have used those values. They already had some values for us, like 1.6 and 1.4. But that's not zoomed in very far, right? This is zoomed in farther. All right. So that's the main idea, really. If you get that out of section 1.5, that's the key. Okay, locally linear. Right in there next to that point, any curve is basically a line. All right, now, if we expand on that a little bit, we learn about a couple of places where we have difficulty. If you look here in your book, right here, absolute value graph. Okay? If we zoom in, and they already have here, and we keep zooming in, is this ever going to straighten? We say the derivative is undefined there. That is not a slope of 0 at this sharp point right here. Because when we zoom in, it will never be a line. And so we'll never be able to pick 2 points that make that slope. Okay? And there's another place where slope is undefined, and we're going to talk about that when we start talking about the other section. Okay? But zooming in will not make that straighten out. So a curve, a nice curve, yes, we can do that. But for these sharp points like that, and those happen in a variety of different curves, we say the derivative is undefined there. The slope is undefined at those points. Okay? All right. So that's basically it for those problems. I mean, that 1.5 in the grand scheme of things is probably the least important of the sections we talk about here. We're going to go on to 1.6. But the concept, the idea of a tangent line and getting in really close, 2 points close together, is a really key concept to grasp. All right? Well, let's look at a couple of the documents that I sent you. So go into your My Documents. And let's pick out, and inside the AP Calculus Period 3, let's grab the one, let's open the one that says Derivative Analysis. Derivative Analysis. Now it says, do you want to say, I can't think of anything you probably need to say. Any document that you had open shouldn't be an issue. Now, I've given you 3 documents today. One of them we're going to use in our homework, but 2 of them are just for you to kind of play with and if you need to grasp any of these basic concepts we're talking about with slope and derivative. So these two documents we're about to look at are essentially things that we've been talking about that you need to have a good grasp of. So if you go to the next page, okay, go to the next page. All right, so what we have here is just a basic curve with a blue tangent line, and you can grab, so you can move the little cursor over that open circle, move it onto the open circle on the X. Move it on the X, yeah, right there. Now you can control click or just hold it down, and the fist will close. If you control click the middle of the touchpad, and now you can slide it. Now as you slide it, it'll change up here whether the slope's positive or negative. Now, there's nothing too earth-shattering about what you see there, right? All right, whenever the blue line is pointing up, the slope's positive. Whenever it's pointing down, the slope's negative. But some of you have asked me about, hey, I'm not very good at sketching those tangent lines. How do you know where to sketch a tangent line? So if you play with this a little bit, you'll get a feeling for, at certain points on a curve, where's the tangent line at? You notice how sometimes at these inflection points, it almost looks like it crosses through the curve. Sometimes that happens. Okay? So just sliding that back and forth gives you a little feeling for that. Okay, so use it however much you want, or don't use it, doesn't matter. Okay, go to the next page. I think there's something to be said for getting your hands on something, being able to, look at it as you need to. Okay, go to the next page. So what this is going to do is take that same idea, and it's just going to kind of highlight the points of the graph. It's going to say, hey, here's the places on this graph where the slope is negative. It's where the graph's going down. And then hit that little up triangle over there. And I think you got to hit it one more time. And then it highlights the places where the slope's positive, which of course is the places where the graph goes up. Okay? So, slope positive in those areas. And of course, it changes at your local max, local mins, right? We've talked about that, those terms, local max, local min. That's going to come into play today in the homework as well. Okay, go to the next page. And the next page. Now we're going to talk about concave up and concave down. Okay, so now when you slide that point along, the words up there will change. It's just going to say, okay, right here where he's at right now is concave up. Now where he's at, it's concave down. Still concave down as he slides and slides. And right in there, it's going to switch to concave up. And what's that called when it switches? Inflection point. It's concave up right now. Right about there, it's going to switch now to concave down. All right? So you can just slide back and forth there, and you can see that. Okay, go ahead and go to the next page. And just like we did before, next page, it's going to highlight. Right now, it's highlighting where it's concave down. And again, you can see it switches at those inflection points. And if you click the up arrow a couple times, it'll show you in red the places that are concave up. Okay, so again, just to really get a grasp of what's concave up, what's concave down. All right, next page, I think that might be it. Is that it? Okay. All right, let's open up the other. The other one that I want to look at is called derivative grapher. Derivative grapher. Yeah, you don't need to save changes. Yeah. Okay. So what we have here is we're going to look at a function that's a cubic function. And we're going to look at a graph of it, and we're going to look at a graph of its derivative. So go ahead to the next page. All right, so up top we have the red graph is the cubic, the F graph, and below it is the F prime graph. Okay, so go to the next page. Now we're going to add the slope of the tangent line, and now remember we talked about that one that Brittany asked about, where we have the slopes of the one graph, and we're going to plot those as y values. That'll be the F prime graph. So go to the next page, and we see the same picture, All right? Now, look where we're at here. We've got, I like how this document lines everything up. Okay? So here we are at this x value of 0.9 whatever, no, negative 3.2. And it's got a y value, 0.939. And this graph down here is a y value, 3.12, but this y value down here is what? The slope of f, right? So this graph is the f graph. This blue line is the slope, right, is the tangent line. So this is the slope of that blue line, and down here we're plotting that point of 3.12. So now, as you hit this little up arrow here, Joe, it's going to move the point a little bit. And now what's happening? Okay, move it one more time. What's happening to the slope? It's positive, but getting less positive, right? So the slope went from 3.12 to 2.98 to 2.205. What did this y value do? It's going down. It's positive and getting less positive, right? Back up to. Click the down arrow again. Let's watch that happen again. Okay? Go back a couple more. Yeah, the down. Yeah, keep going back. Okay, stop there. Okay, now get ready to hit the up arrow. So, as this dot, see, we've been talking about this now for a few days now, haven't we? As this line moves, the slopes are still positive, right? But, so you can see the importance of that last document. So understanding when's the slope positive, when's the slope negative. Slope's still positive, but it's getting less positive. So these y values are positive. They're above the x-axis. They're positive, but getting less positive. Okay, so keep hitting the up arrow. So positive and getting less positive, right? And then, of course, the slope here is what? 0, okay, which is a local max. And look what happens down here. Crosses the x-axis. It's an x-intercept. And now what's going to happen to our slope here? Negative get more negative. What's this graph going to do? Its y values are going to be negative and get more negative, right? So we keep going. We keep going. We see the blue line. Negative slope getting more negative. Negative slope getting more negative. This graph's negative and getting more negative. Going down. Till we get down here. Now, when we bottom out down here, what's happening up here? Isn't that the inflection point? Isn't that the inflection point? Think about it now. The slope is, it's going down, down, steeper, steeper, steeper. That's concave down, right? But what's about to happen is these slopes are about to still be negative, right? So go ahead and hit the up arrow now. They're negative, but they're getting what? Less negative. You're talking my language. So negative and getting less negative. So what are these y values? Negative and getting less negative, right? Which are coming back up. Okay? So that was the inflection. So this local minimum, right? F prime has a local minimum, and that turned out to be the inflection point up here. One of our jobs this week, and will happen one of the next couple days, is we're going to make kind of an organizational chart of all these things we keep talking about. Because there's so many interconnections here, we need to really organize. So look at this, local minimum, back to an x-intercept.
All the roots of prime are the max and min.
It seems like so far the roots of f prime seem to correspond to these max and mins here, right? Now, there's a little more to the story than that, but so far that
Inflection points are the
inflection point of f seems to be a minimum, or it could be a maximum if we had a different graph of that. That is definitely one of the connections we're going to have. Okay, there's a little more to it than that, but that's exactly right. So we got a 0 slope, and now it's about to become positive and get more positive, so this graph is going to go up. Okay? All right, so there you go. So it's a really cool little exercise to just move yourself back and forth to kind of see those connections. All right, is another page, or is that it? I think that might be the other page. All right, so a couple of things for you to just look at and kind of go back and forth with and see if it makes sense to you as you need to. All right, if you turn to page 55 in your book, page 55 in your book, I just have a little bit to talk about in this section. This section we're going to spend about 3 days in, and we're going to have some assignments on the calculator as well. So we're going to take a piece at a time and make sure we understand it. And so if we look at page 55, they have a picture very much like the picture you're looking at on your calculators. If you go to that right there, oh, you know what? I skipped a really cool. I skipped a really cool part of section 5 is one of your homework assignment problems. E to the x. What do you know? What happened on e to the x? The derivative on the e to the x graph, the slopes are the same as the y value. So that was really cool yesterday when we saw the slopes of sine, when we plotted them, made the cosine. This is another really cool thing. A lot of people say, what's this important about e? What's the magic of this e? Well, here's one of the really cool things about it. It's the only function, e to the x, where its slopes are the same as its y value. So it's its own derivative. So the derivative of e to the x is e to the x. The derivative of sine x is cosine x. The derivative of e to the x is e to the x. 2 to the x doesn't have that property. 3 to the x doesn't have that property, but e to the x does. Okay? An easy one is right here at 1. This has a slope of 1. It's got a y value of 1. And what happens? The y values get bigger and bigger and bigger, so do the slopes. Bigger and bigger and bigger. So that's a really cool property of e that was in one of your homework assignments. Okay, so then we're back to this. Now this is very much like the picture that's in that document I just gave you. Talking about, hey, look how A has a local max. It corresponds to that root right there. C has a local minimum. Corresponds to that root right there. Your calculator assignment today is going to have you investigate this a little more. This whole idea of how this goes from positive to negative here means that this graph was going up and then going down, and how that makes it max. Okay, so you're going to get into that a little more. And then, like we said, this inflection point seems to correspond to that down there. So, same thing we were just looking at on the document. So that's on page 55. The other thing that you notice in 55 is a whole bunch of words and terms. Now, local max, if you look through all those bold-faced terms on page 55, we've talked about almost all of them. Local max, local min, inflection points, concave up, concave down. There's one in there that I do want to have you write down here in a minute, but we should already know those terms. Now, there is another term that I don't think will be on your homework, but I do want to talk about it real quick. On page 58, the top of page 58, it talks about something called a global max and min. A global max and min. Now, a local max and min, local means in a very small region, global means in a very large region. So a local max min, well, very simply put, you could have okay. Okay. And that graph in that interval right there, how many local maxes does that have? 3. How many local min? 2. Okay, the peaks and the valleys. What's the global max? Global max means the highest point. That's the global max. There's only one global. And what's the global min? It's actually that left endpoint. A global max or min could be at an endpoint. It could be at a local max or min, but it also could be at an endpoint. A global max and min, or excuse me, a local max min is never at an endpoint. A local max min is always a peak or a valley. Okay, kind of a thing. All right. Another thing I wanted to mention about that is this idea of it talks about a local max value versus a local max point. If I ask where is a local max, I want to know the x value. I want to know its input. If I say what is the local max value, we want its output. So there's a big difference. Where is the local max means its input. What is the local max, or what is its value, means the output. Now normally with local max and min, we want the input. We don't know where they are, because like that one had 3 of them, so we don't know where each one is. We don't really care about what their value is. But global max min, we usually care about the value, the output. What is its highest point? What is its lowest point? We want to know the y value. Okay, so that's something we'll talk more about, but that's kind of important. All right, so the main thing I want to define for you today then are two terms. First one is this. A stationary point of f of x, okay? A stationary point of f of x is where f prime of x equals 0. A stationary point of f of x is where f prime is 0. Now what we normally mean is the input. We want to know the x value. Where f prime is 0. So at x equals 2 or x equals negative 1. We now careful with, don't say no slope. 0 slope. So that's exactly right. A stationary point of a graph is where its slope is 0. Now, there's three of them. There's three types of stationary points. One would be a local max. Oops, that's terrible drawing. Slope is 0. What's another one? Local minimum. Slope is 0. And this is where what Natalia was talking about with those roots and so forth. This is the one we sometimes forget about and we'll be talking more about. If you had a graph like x cubed, it could have a slope of 0 and not be a local max or local min. Now, so this one we call local max. This we call local min. For lack of a better term, we're going to call this a flat spot. Now, you could argue that the first two are also flat spots, but we're going to call those local max, local min. This one we'll call a flat spot. It's a place where the graph flattens out just momentarily, but then continues in the same direction and does not go back down the other way. Now, that also is an inflection point, isn't it? This point right here, this flat spot, happens to not only be a stationary point, because the slope is 0, but it's also an inflection point. But now, remember, not all inflection points, though, are flat spots, like on sine, right? There's an inflection point right there, but its slope is not 0, right? So this flat spot right here, like on x cubed, the basic x cubed graph, is a stationary point because the derivative is 0, slope is 0. But it's also an inflection point because it changes concavity there. So it's possible it could be both. Okay? But those are the three possibilities if the derivative is 0. There are no other possibilities on a graph where you can have the slope be 0. Okay? It's got to be one of those three. All right. Now, the other one is that I want to talk about is a critical point of f of x. A critical point of f of x. This is where f prime of x equals 0 or f prime of x is undefined. So stationary point is a subset of critical point. Like a square is a subset of a rectangle, right? You know that old thing, is a square always a rectangle? Think about it. Is a square always a rectangle? Yes. Is a rectangle always a square? No. Is a stationary point always a critical point? Is a stationary point always a critical point? Yes. Is a critical point always a stationary point? No. Okay? All right. So if something is a stationary point, the derivative is 0. So these three spots here are stationary points. They're also critical points. So we could list those. Might make it sense. Okay? So where f prime is 0 would be your local max, your local min, and your flat spot. So those would be, that's not really a flat spot. Anyway, those would be critical points right there, the three places when f prime is 0. But then you'd also have those places when f prime is undefined. Now that means the slope is undefined. Now what's one of them we've already talked about? Absolute value. Where the slope is undefined. Right? at that sharp point. Now there's other types of sharp points. Like you could have a graph that goes up and then kind of changes like a piecewise function and does that. Again, the slope is undefined there. Any kind of sharp, abrupt change. You could even have a graph that kind of was a parabola and then did this. Right? There are graphs that do that. The derivative is undefined at those sharp points. Why? Because if we zoomed in, we would not be able to straighten out. It would not make a line. So the slope is undefined. You have an abrupt change, sudden change in slope. So at that point, the slope is undefined. So those are called critical points. Now, this one is also a local max, though. Okay? To be a local max, it does not have to be a smooth curve kind of a thing. This is a local max. In this local small area, this point is the highest point. And this would be a local max right here. You'd have a local min down here. You have a local max right here. Peaks and valleys. Is this a local max? No, because it comes up and it keeps going up. So this is not a local max. That's a local min. Okay. But now you also, what's the one you learned in algebra class when the slope's undefined? What kind of a line has a slope that's undefined? Vertical line. Vertical line. Here's the graph of x to the 2/3. Or this is x to the 1/3 actually. X to the 1/3 looks like that. Right there. It's got a vertical tangent. Okay? The slope's undefined there too. That'd be kind of the inverse of a flat spot. Right? A flat spot where you have a horizontal slope. It's possible you can have a graph like that that has a vertical slope. So, sharp points, the slope's undefined, and at vertical tangents, the slope is undefined. So those would be critical points. Those would be critical points, okay? But not stationary points. Stationary points just what we do. Okay, so that's a term we use a lot. We use stationary points a lot more than we use critical points, okay? As we're learning this stuff about slope, we'll usually concern ourselves with nice functions that don't have sharp points and vertical tangents and weird things happening. We'll only get into those as we get better at what we're talking about, and then we'll bring in the messy stuff. But for a while, we'll work mostly with just nice smooth curves, okay? But there may be a few questions about some of these and so forth. All right, so I'm going to give you the rest of the time. There's 2 assignments, and actually neither one of them take a whole lot of time. But really focus on understanding what's going on. So 1.6 day 1. So what I've done is broke up 1.6 into some smaller chunks so we can do some other stuff along the way. So you're going to do 1.6 day 1. And then you're going to do this, and you can do this in any order if you want to do the calculator stuff first. You're going to do this worksheet, which has you open up the other document I sent you. It's called First Derivative Test, and it says it right on here. You're going to open up the document called First Derivative Test, and you're going to follow the directions on this worksheet front and back and fill in these and answer these questions. Okay? So 1.6 day 1 and the worksheet with the document. Okay, you have the rest of the time to work.